Hello everyone, my name is Seshagiri Prabhu. I'm a PhD candidate at University of Louisiana at Lafayette. I'm presenting a paper titled Recovering Structure of Input of a Binary Program. Okay, the problem which this paper is trying to address is given one or more inputs and a program that accepts that input data, how do we recover the structure of the input? So let's look at the example program that we have on the left side. So this program reads the input, which is a comma separated value given at the bottom. And in this program, at line 2, it reads every line that is separated by a new line character. And at line 3, it reads an integer that is a counter. And using that counter value, at line 4, it allocates an integer array. So the counter value determines the number of elements in that integer array. And later on at line 6 and 7, it reads the remainder of the string in that line. And those are like comma separated value, and they are integers, and they are read into that array that we declared at line 4. And later at line 8 and 9, it sums up those values in that array and prints that. And on the right hand side, what you can see is the structure of the input. It's a state machine representing the space of acceptable data for the given program on the left side. And so, okay. So each node in that state machine represents a field, or let's say the first node, the start node, is the value of that, or the representation of the counter, and followed by the comma that follows that counter value 2. And the next node represents digit plus, which is the token expression of the values 78 and 35 in that array. And each of those values in that array. Okay. Am I audible now? No? So the mic may not be working? No.
Yeah. Can you try now?
Am I audible now?
No. Yeah, usually.
Oh, so the mic was turned off.
Yeah, okay.
Okay. Now let's see, why do we need these input structures? So in traditional fuzzing, random data is generated and fed to the program in a way to crash the application of the program that's been under test. But most programs requires input to have certain structure. So if we create random data where the program expects structured input, then the program may handle those, they may not accept the data, and they may throw syntax errors. So, and whereas in grammar-based fuzzing, the fuzzer expects us to provide a grammar, and it generates quality inputs based on the grammar that we specify, and it produces either crash or improves the coverage, as in the case that is proven by AFL Smart, a paper from 2019. And so for the grammar-based fuzzing, we need to provide the grammar. And where do we get the grammar from? Most of the cases, the grammar are not available. Developers, they don't publish the grammar online. And even if the grammar is available, it may not be up to date. And if the specification may be available, but it may be in text format. For instance, the specification of the PDF, it spans over like 800 pages, which is like another PDF. And sometimes the implementation, the grammar may be available, but the implementation may accept more than what is specified in the grammar. So said that solving this particular problem would require us to solve these subproblems. One is how do we identify the values? That is, input is a stream of bytes. How do we chop the stream of bytes into smaller subsequences where each subsequence makes certain sense? For instance, for the comma separated value, there are at least 6 values, and the next challenge would be how do we identify fields from that stream of values or stream of input bytes. So we need to group values that belong to the same field. For instance, in the case of the CSV, which we have seen, bytes 78 and 35, they belong to the values of the same field. And using the identified values and the fields, the next step would involve constructing a state machine where each node in the state machine represents a field. And if there are multiple values for a field, we need to generalize them to create a regular expression token. And let's say if you have multiple inputs to the same program, how do we join different state machines to create a unified state machines? That's another challenge. So again, there are a few more challenges. Those are related to identify different types of input. Broadly, there are 2 different types of input types. One is atomic fields. Those are like of type atomic when it comes to the programming language that we are using. So atomic fields could be fixed length. They could be fixed length. For instance, on the right-hand side, you can see the BMP image example, where all the fields of a BMP image header are fixed length fields. And when it comes to variable length fields, except the delimiters and the separators of a CSV, all of them are like variable length fields. And the composite fields are fields of collection of fields. For instance, a record is a composite field. It's a sequence of values of different types of fields. For instance, if you look at the pixel 1, it is a record. It consists of 3 different fields that specifies the value of red, green, and blue of a given pixel of a BMP image. And arrays are sequences of values of the same type of field. For instance, 78 and 35 of the CSV row they are of same type, but they are different values of the same field. And there is another set of composite field called variant record. Variant record is the sequence of values where a value specifies the type of record that are following that particular field. Now, let's look into our method. So our method relies on the existence of a dynamic taint tracking tool. So our taint tracking tool, it tracks the flow of input bytes through the program. And we have implemented a taint tracking tool that taints every byte in the input. And a taint consists of the offset of the byte in the input. And while executing the program with the given input, it produces a taint trace. Taint trace is a sequence of tuples consisting of the instruction address and the set of taints that are accessed by that particular instruction during an invocation. For instance, if you look at line I4, it accesses the byte 2. So in the taint trace, there will be 1 instance of I4, whereas I7, it appears 2 times in the trace. During its first appearance, it accesses it will have the taints of the byte 78, and during the second invocation, it will have the taints of byte 35. And once we have the trace, we apply the first heuristic, which says that 2 contiguous bytes of the input constitute the same value. There exists at least 1 instruction that accesses those bytes together during one of its invocation. So for instance, at I4, it accesses byte 2, which means 2 can be potentially a value. And at line I7, it accesses 78. So 78 can be another potential value. And the comma that follows 2 is accessed at line I3. So that can be another potential value, and so on. So we split the input at this stage. At the end of this stage, we split the sequence of bytes into sequence of values. Next is we apply another heuristic. We say that two potentially non-contiguous bytes of the input, they constitute the different values of the same field if those bytes are used by exactly the same set of instruction, like exactly the same set of instruction. For instance, byte 2 is used exactly by I2, I3, and I4. And byte 78 and 35 are used at exactly I7 and I9. And the byte comma that follows 2 is used only at I2 and I3. So irrespective of different data you provide, the bytes at those particular data would remain the same. The number of instructions that accesses those bytes would remain the same for a given program. And now we have a sequence of fields. We identified that the bytes 78 and 35, they belong to the same field because they were accessed by the same set of instructions, but during different invocation. And remaining values are all different fields. And now we have like this input byte, we can specify them as a sequence of fields. And each field, to construct a state machine, we take out each field and then we create a node for that. And the edges for that state machine reflects the consecutive ordering of the fields in this sequence. Let's say if there will be an edge from F1 to F1 to F2, F2 to F3, F3 to F4, and then F3 back to F3, F4 back to F3, and the final node is the F5. And let's say if there is a node that contains more than one value, which is the case of the node F3, we need to generalize them to create regular expression tokens. For instance, 78 and 35 are ASCII values, ASCII decimals, so they are generalized. The 7 and 3 are generalized to digit, 8 and 5 are generalized to digit. So it becomes digit. Now, there are more salient features of our method. The first one is recovering complex structures. So once we have the trace contains the set of taints. We represent them as a taint interval tree. And then using the taint interval tree, we represent the taint interval tree using a subsumption relation, like taint, like the interval trees subset relation. And we extract the frontiers, or we take the frontiers of taint interval nodes. Those becomes a sequence of fields. And using those sequence of fields, we construct a state machine. And we do those for each level at the instruction, at the taint interval. So we find multiple state machines. And when we do it recursively, we get a recursive state machine where there'll be a node that may contain another state machine. And that state machine would represent the nested structure. So that's how we represent the input with nested structures. And calling that nested structure would be similar to, analogous to a procedure call, where when we transition from one node to another, we'll be calling that particular state machine within that node. And then while exiting that state machine, it would be like procedure return. And we are not done with that. We get RSM for each input. Now we know that each node in an RSM can be identified using a set of instructions, because a field we identify using a set of instructions that accesses the values of that field. So let's say given multiple inputs to the same program, we get multiple RSMs. We can join them where the nodes matching same field can be matched together, they can be unified, and then we can create a unified RSM representing expressing the state of data acceptable to a given program. And when it comes to evaluation, so we studied different data formats like PNG, PE, etc. And then we identified 6 structures in them. And we also identified that they are using 2 types of data encoding, ASCII and RAW. And we also studied the source code of the programs that were processing or accepting these inputs, these data formats. And we identified that there are 8 different methods of access. And using this combination of methods of access, we hand created a few programs to demonstrate that we can recover the RSM of these programs. of the input to these programs. And to evaluate, we use two methods. One is we manually evaluated. We generated the RSM using our algorithm, and then we compared with the expected result. And for our manual evaluation, we identified that the RSMs are syntactically valid for all the subject programs. And our method correctly identified fixed length fields, variable length fields, arrays, records, and variant records. We programmatically also evaluated. We did a graph traversal, generating new data. We generated 1,000 new data for each RSM and then fed them to the original program. The acceptance rate of except three subject programs, all the other programs, the acceptance rates were 100. For these three programs where the acceptance rates are low, is because they have fields that encodes the length of other field. Say there is a counter and it controls a variable length field or array. So right now our system, it syntactically identifies the fields. The field identified, the RSM is syntactically valid, whereas it doesn't learn the semantic constraints between fields. So this is a real world example. The subject program is objdump, helpful in disassembling executable files. And the input to the subject program that we have given was an ELF binary. And on the right hand side is the graph that our system generated. It has the highlighted sections are the 4 important sections of the ELF binary header, instructions, and section names. And to conclude, so we proposed a new method to recover RSM expressing the data acceptable by a program. Our method identifies fixed length field, variable length field, arrays, records, and variant records. The RSM generates syntactically valid data. And we also have a method to join multiple RSMs and create a unified RSM. Thank you.
So you also you have to provide
we haven't made a study about the optimization. Right now, all our subject programs, we had like 0 optimization, but it also depends the way the program reads. It also depends how we extract the structure from that, because we identify the values from the taint trace generated. So depending on the way the program parses the input, we will know. So we are working on that. In our next paper, we would have certain results on that too, certain insights on that. So is it okay?
So if I'm understanding this correctly, right? Essentially, like what your system is doing is it's learning a regular language for the inputs of your program, right?